Thank you for joining us today. My name is Ben Weiss, and I'm working with CEVA as a vision expert in the Customer Solution Group. Today, I would like to present a new and innovative technology, the CEVA SansFlow. SansFlow is the first high-performance sensor hub DSP architecture to fuse data from multiple sensors, including cameras, radar, LiDAR, time of flight, microphones, and inertial measurement units. Up until now, CEVA's focus has been on creating solutions that address both wireless connectivity and smart sensing. We've created products that focus on these individual technologies, but as we see more and more smart devices utilizing many different technologies coming on the market, we've realized that our products must be able to process multiple sensor types as well. We decided that we needed to develop a product that can support many different sensor types. Our strategy now is to build components that can be utilized across multiple applications and sensor types. We are now moving to a more holistic approach to combine different technologies together. SansFlow is the industry's first high-performance sensor hub. A sensor hub processes and fuses data from multiple sensors and enables designers to create smart devices. These smart devices usually process data from multiple sensors, such as cameras, radar, and LiDAR, which are used, for example, in automotive applications, or sensors such as time of flight, wide-angle cameras, microphones, and inertial measurement units, which are used, for example, in smartphones, laptops, and tablets. These types of sensors produce data that must be processed by combining both scalar and vector processing, floating point and integer data types. In addition, traditional methods of analyzing the data must be complemented with deep learning capabilities. With such a large variety of applications, it is important to have an architecture that can fit from both a performance and cost standpoint. SansFlow is highly configurable and self-contained. It has the capacity required for sound, imaging, neural network inference, radar, and SLAM. It incorporates the CEVA BX2 Scalable processor for control execution. SansFlow has three different configurations: SP250, SP500F, and SP1000, which will be described later. SansFlow is a highly capable architecture that provides high performance per watt processing to address both single and multi-sensor context-aware designs. It can be utilized for computer vision processing via both traditional methods and deep learning methods, and also has capability for SLAM processing with high-performing floating point units. The SansFlow architecture is modular and scalable to fit products in different markets. In addition, it is complemented with a mature software infrastructure for neural networks, computer vision, sound, and sensor fusion. Compared to our previous generation, CEVA X and 6, SansFlow delivers a much more efficient solution in both size and power. As I mentioned in the previous slide, we can compare some performance metrics to the CEVA X and 6. However, SansFlow is much more than a computer vision DSP. SansFlow is an evolution of Sivir products and builds upon CEVA's successful legacy of creating leading neural network inference engines, computer vision DSPs, audio DSPs, and highly capable scalar processors. SansFlow takes the strength of products like NeuPro, CEVA XM, and CEVA BX2 and combine them into a high-performance sensor hub. Our solution is flexible and scalable to accommodate different market needs. We can customize the DSP from both an area and power standpoint, as well as balance between fixed point and floating point processing workloads. To keep high utilization of the DSP, we provide a multitask mechanism to switch between AI tasks and different sensor processing tasks. Contextual awareness is the ability to gather information, analyze it, and adapt the behavior accordingly. In today's market, many different types of sensors are being integrated into smartphones, robotic, automotive, AR/VR headset, voice assistants, and smart home devices. The idea behind integrating so many sensors is to gather as much information as possible about the surroundings and to create a smart device that can adapt its behavior based on the user behavior and the changing environment. Analyzing data from all of these sensors is not an easy task. Some algorithms need to be processed, each sensor independently, while others need to fuse data from different sensors or to run a neural network on the data. This type of application requires a new type of processor architecture, the CEVA SansFlow Sensor Hub. The SansFlow architecture is designed to be a fully configurable and address the needs of different markets. Overall, it is 7 times better in performance per area compared to our previous generation CEVA XN6, and more than 4 times better in floating point acceleration. The architecture combines both scalar and vector processing unit, as well as a rich instruction set to accelerate a wide range of algorithms. From complex linear algebra tasks for radar or LiDAR and SLAM processing to 2D or 3D classic computer vision and deep neural network inference. All of these algorithms can be executed on the same DSP with high utilization and extremely low power. The new technology can reach a frequency of 1.6 gigahertz. Integrated with the CEVA BX2 DSP for scalar processing, SansFlow can attain much better utilization of control code execution. With 400 gigaflops, a new pipeline for floating point vector processing with very short latency and full complex data support, SansFlow can efficiently run typical tasks for radar, LiDAR, and sensor fusion. Binary neural network inference capability are also fully integrated and provide up to 20 TOPS. The new memory architecture can handle up to 400 gigabytes per second data bandwidth and include a 4-way instruction cache and a 2-way vector data cache to easily port the user code to the DSP. SansFlow has 2 identical load store units, LSUs, that provide a wide access to the internal memory with up to 2048 bits load and 1024 bits store per cycle. With the parallel load store capabilities, SansFlow can efficiently accelerate algorithms with random access to the memory. The vector computation units, VCUs, are fully configurable and include up to 1024 max of 8-bit by 8-bit. 2 identical units, VCU0 and VCU1, perform MAC-based instruction, and additional light VCU executed any non-MAC instruction in parallel. Both VCU0 and VCU1 include an optional 32 or 64 single precision floating point max and nonlinear units. Overall, the new redesigned SansFlow pipeline can reach up to 20% speed up and extremely low latency between instructions for efficient vector code execution. SansFlow has 3 different configurations: SP250 with 256 max of 8-bit by 8-bit and 64 max of 16-bit by 16-bit, mainly for vision and audio domains; SP500F with 512 max of 8-bit by 8-bit and 64 floating point max, mainly for vision and SLAM algorithms. The last configuration is SP1000 with 1024 max of 8-bit by 8-bit and 256 max of 16-bit by 16-bit, mainly for AI processing. These different configurations enable SansFlow to scale in terms of performance and area for a broad range of products and markets. SansFlow has 2 identical computational units, VCU0 and VCU1, while VCU1 is optional. Each one supports fixed point, floating point, and nonlinear capabilities. The fixed point ALU has flexible MAC operations to support vector operation for wide range of use cases and data types. It includes arithmetic, logic, bit manipulation instruction, as well as dedicated spatial instruction to accelerate specific algorithms from different sensors. The nonlinear unit includes native support for Taylor series and Newton-Raphson approximation, with flexible trade-off between accuracy and speed. The floating point units have native support for single and half precision vector operation, real and complex vector data types, and intra-operations. Each floating point unit contains up to 32 single precision max or 64 half precision max, and supports both real and complex vector representation and vector processing. All floating point operations are IEEE 754 standard compliant and support several rounding modes. Double precision floating point is supported using dedicated instruction in the scalar unit. The new redesigned SansFlow floating point pipeline provides extremely low latency between MAC commands for efficient radar processing, SLAM bundle adjustment, and complex linear algebra algorithms. Binary neural network inference is a new and innovative feature in the architecture. Each VCU can perform up to 1024 operations of 8-bit by 2-bit or 3072 operations of 2-bit by 2-bit. With both VCU units activated, SansFlow can achieve up to 20 TOPS for binary neural networks. The CEVA Deep Neural Network (CDNN) software framework provides customized quantization and can reach the perfect balance between performance and accuracy. SansFlow comes with software and libraries for different use cases. For example, 2D and 3D imaging, wide-angle imaging, SLAM, radar processing, neural networks, software and voice processing, and sensor fusion. The software package is fully optimized for SansFlow and enables easy and simple porting of the user proprietary code to the DSP. SenseLink is a unique software solution for linking all CEVA technologies to the host processor operating system for easy integration with the user application. The CDNN, CEVA Deep Neural Network solution, include optimized runtime libraries for SansFlow, as well as an offline inferencing graph compiler. The graph optimization process include accuracy optimization from floating point and fixed point, layer fusion, retraining, as well as scaling per layer. The software is fully optimized for all CEVA processors, including the new SansFlow Sensor Hub, and support over 200 different neural networks. CDNN Invite is CEVA's technology for seamless integration of SansFlow with a custom DNN accelerator. The CDNN can take any pre-trained neural network and compile it to a runtime execution plan that is fully optimized for the SansFlow. The graph compiler supports precision optimization from floating point to several bits, layers and tensor fusion, memory and bandwidth reduction, retraining, and multi-stream execution from multiple sensors. SansFlow is the industry's first sensor hub architecture and provides dynamic processing for multi-sensor and multitask context-aware devices. It can process many types of sensors, from cameras to radar and microphones. The modular architecture can fit design needs in terms of cost, power, and performance, and provides efficient performance and area. It is complemented by a comprehensive software stack that includes optimized software libraries for different sensors, SenseLink for easy task offloading from the host processor to the DSP, and the leading CDNN graph compiler for neural network inference. Thank you so much for your attention.
Thank you, Ben. We'll go to the Q&A now. Okay, had a few questions of my own to start on the architecture. I know we've been talking about this, preparing for the conference, but maybe you could help break this down. You've got the BX2 is a part of all the SansFlow configurations, correct?
Correct.
When CEVA announced that it was positioned as a hybrid scalar DSP, does it still have vector capability of its own? It was described as a 5-way VLIW.
Yes, so the SansFlow is combined of scalar units, and these scalar units are exactly the BX2 units.
So how would you divide the workload then? What would you run on the BX2?
So the BX2 can be offload any scalar processing. It can be control code, and it can be audio, speech, voice, algorithms that doesn't really need the vector processing and the heavy floating point capabilities. And this way you can keep the power extremely low when you process a low bandwidth and very light processing. While when you want to switch to AI or image processing or heavy complex floating point acceleration, you can enable the VCUs and the power level will be higher, and this way you can accelerate much heavier algorithms.
Okay, what is the vector width for the VCUs?
So it's 1024-bit vector, and you can load store up to 2 vectors like this.
So that per VCU?
It's per LSU and per VCU. So the VCUs and the LSUs, they share the same vector register file.
Okay. And so if you have two VCUs, then they operate together as a
Correct. Yes, correct. So they operate together. Actually, we have three VCUs. Two VCUs are for Mac-based operation, while we have additional third VPU. We called it a light VPU that can offload any non-Mac-based operation. It can be permutation, bit manipulation, any condition that you need to do in parallel to the two main VCUs. So these three units can work in parallel in the same cycle.
Got it. And so you've shown that it is very highly configurable, but you're initially going to launch with 3 pre-configured models?
Right.
And so what's the reason for that versus just letting people pick and choose?
So first of all, we identified different markets and different markets needs. And for each market segment, where we have a dedicated configuration. As you said earlier, we have customers that are more oriented to vision and audio processing. Some customers are oriented to SLAM and vision, and some are oriented more to vision and AI. So we have 3 segments, and for each one, we have this configuration that is suitable exactly for his needs.
Okay. And then at some point, you'll provide more options for configuring.
Yes. This is the general configuration. Of course, we can play and we can create customized solution for dedicated customers, but these are the 3 general configuration we support.
Okay. And do those configurations come with a nonlinear unit?
Yes. So the 2 VCUs, VCU 0 and 1, they have the Mac operation, they have the floating point unit, and also they have the vector nonlinear units. Okay. And the units, they can run any Taylor expansion, or we have a dedicated hard-coded instruction for vector processing in floating point and fixed point for nonlinear operations.
Okay. I'll take a few of the questions that we've got from the audience now, and any of the attendees, go ahead and submit your questions in the Q&A box. I think you probably showed this earlier in the slides, but when you're comparing to the previous generation, it was all ISO process, correct?
Yes.
The performance comparisons.
Mm-hmm.
Okay. And then there's a question on if you could maybe go into a little bit more detail why the VGG benchmark improvement was so much greater than, say, for matrix multiply.
So as you know, matrix multiply, first of all, it's a floating point benchmark. And for floating point, we have 5 times better performance acceleration because we included 4 times more floating point max in the system. Now, the VGG is based on 8-bit max, and for the 8-bit max, we have much greater factor. So these are different groups of benchmarks. So we have benchmark for floating point acceleration with up to even more than 4 times better, because we have a shorter latency now in SansFlow comparing to our XM6. So you should expect for floating point algorithms a little bit more than 4 times better performance. But for fixed point, we have the factor between XM6 and SansFlow is much higher, and this is why VGG can get a much higher performance boost.
Makes sense. Could you say how large are the caches and the closing couple memories?
So I think this is something that we can this piece of information we can provide during the breakout time. We have different configuration for the internal memory sizes. This is not something that I included in the slides, but this is definitely something that we can answer later on. Okay.
Maybe we talk a little bit more about the binary network. We've been hearing now a few times about that, but I think you're the first to actually have that built into your architecture. So it's a little bit different, I think, for BNN. And when you talk about ops, it's more of a bit manipulation. How is that handled in your VCUs?
Okay, so first of all, we have 2 VCUs, and each one of the VCUs can support binary neural network inference. And I think The way we accelerate it is actually we have a dedicated hardware to run the atomic operation for binary neural network in 8-bit by 2-bit and 2-bit by 2-bit. So these two modes are actually mapped to a specific instruction set, primitives, and also mapped to a dedicated hardware that you can find in both VCU 0 and VCU 1. So this is extra logic that we integrated inside, and we wrapped it up with a dedicated instruction set.
Got it. And the 2 bits, is it just 1 bit, 1 or -1, the sign bit?
It's 1, -1, and 0 also.
Okay, so ternary.
It's ternary, yeah. Actually, it's ternary. You can use it for binary networks and also ternary networks. We provide just more flexibility. We found that we can get much better accuracy 2-bit by 2-bit with practically more or less the same area and power consumption. So it brings more flexibility and more accuracy to binary neural networks.
Good question. I asked, I think the previous speaker, you showed your support for the different frameworks. Mm-hmm. Is there some different process you have to go through for training a binary neural network?
Mm-hmm.
Do you have different software specifically for that?
No, so we have the same software. So we have one software. This is the CDNN, CEVA Deep Neural Network. And this is a graph compiler that can handle a variety of neural networks. So we can deal with floating point, with fixed point. And of course, with the SansFlow, we will provide graph compilation and accuracy analysis for 1-bit and 2-bit based networks.
And quick question on your release date. I think you said third quarter?
Yeah, yes, correct, yes.
Right. Could you provide any guidance on the power consumption for an AI use case running at 1 gigahertz?
Not at this scope. I think under NDA we can disclose this information.
Never get power out of you guys. Okay, this was kind of a long question. Besides parallel processing for different sensor inputs, are the different processing units blocking each other to fight for the common resources like load store?
No, they can all work together. 2 LSUs, 3 VCUs, and the scalar processing unit, they can work together in the same instruction. So there are no blocking between units.
Maybe a quick question, maybe one more before we wrap up. Talk about sensor fusion. You mentioned LiDAR, radar, computer vision, but
right.
Some of that's more fusible than other data. I mean, can you really run LiDAR processing and vision processing at the same time?
Yeah, so I think running radar, LiDAR, vision, it's all about, first of all, the native data types that you support. Of course, with LiDAR, radar, you have a much broader dynamic range, and therefore we mapped all the native C++ data types to the scalar and the vector processing intrinsic. So once you work with complex, for example, complex data types in scalar, you can scale it to vector and you can run it, and each, for example, complex MAC is mapped to a specific intrinsic on the system. So I think it starts with the native data type support, and it goes also to the instruction set. So we have dedicated instruction set that are customized or tailored for specific algorithms in radar, in SLAM, in computer vision, and in audio. So if you take a look at the instruction set, you can see groups of instruction set that are targeting specific algorithms. So this is the way we can switch between different tasks, and we can have very good utilization on each one of them.
Okay, thanks, Ben. We're out of time, but look forward to talking to you in the breakout session.
Thank you. Thank you very much.